fascinating problem here, at least from a standpoint of just algebraic manipulation. We're trying to establish that this expression, a to the fourth, or we're trying to find out when a to the fourth plus 4b to the fourth, where a and b are natural numbers, is prime. Now, just to be clear on the natural numbers, by that we just mean 1, 2, 3. It's often called positive integers these days, but 1, 2, and 3 are called the natural numbers. 1, 2, 3 ad infinitum. It's supposed to be a 3 if the Wi-Fi will just work for us here. Okay, so that's 1, 2, 3, ... Now, we have a kind of a sort of a standard trick in math. Sometimes in math, you just add 0 in a clever sort of way, and then that helps you take advantage of certain algebraic identities. That's what's going on right here. This object right here that I'm hovering over is just equal to 0. Notice 4a squared b squared minus 4a squared b squared is just 0. So we haven't actually changed the equation because we've just added 0 to take advantage of an algebraic identity. Now, if you look at this binomial squared right here, I'm going to use different letters here. I'll just use capital A. Okay, so we'll have this part right here would be capital A plus B quantity squared. And of course, cap A would be little a squared, and then cap B would be 2b squared. Okay, and now you'll notice that right here, that's exactly what these three terms are. Right here, this would be your cap A squared right here. Oops, lost the pin here. Okay, that would be the capital, there we go. Okay, so we have A squared right there. This would be B squared, because that would be 2B quantity squared. Okay, and this part right here would be your 2AB. And I know you guys probably saw that, but that's really what we're using, just the standard binomial squared result. And again, your choices of A and B would be little a squared, and B would be 2B squared, okay? Now notice we still have this part left over and unaccounted for. Okay, we have this part is unaccounted for, and so we just had to recopy it. But this a squared plus 2b squared quantity squared accounts for this term, and this term. Okay, now let's clear this out. Okay, now the next piece of this, okay, is noticing that this is actually a squared minus b squared right here. Okay, so this is in the form a squared minus b squared, where b is actually just, b is going to be capital B is just equal to 2AB, 2 little a little b. Yeah, I apologize, the Wi-Fi sucks here. Okay, so if you square this, you get 4a squared b squared. Okay, now notice that's exactly what we did right here. A squared minus b squared is equal to a plus b times a minus b. It keeps cutting out, y'all. I apologize. It's going to take a little longer than usual. It's very substandard Wi-Fi in this part of the world. But you have a plus b. Whoops, there it goes again. Okay, a plus b times a minus b. And that's going to be happening on this very next line. Okay. Okay. Now, and again, that's exactly, y'all, this right here would be the a plus b portion, where a is just equal to a squared plus 2b squared. So this is this piece right here corresponds exactly to this three-termed parenthetical expression here. And then this would be your a minus b. Okay. Now, one more time, one more round of algebra. And by the way, y'all, all this algebra is credited to Sophie Germain, I believe. But when you expand a plus b squared, okay, you get almost all of this, but you would just have b squared. So that's why we have to add another b squared here. Okay. So again, this is the a plus b identity. Again, a plus b quantity squared, but that only gives you b squared. But since we have 2b squared here, you have to chunk in another b squared here. And in a similar fashion, we get this expression right over here. Okay, now finally we can get to the result. Now notice we were looking for all the a's and b's. We have this thing factored after about 1 million years of struggle here. But if you notice when a is equal to 1, when a and b are equal to 1, I'll write it this way, just, okay, when a and b are equal to 1, okay, notice that this part right here, if a and b are equal to 1, this part evaluates to 0, and so we actually get 1. Okay, 1 right here, and then if you substitute a equals b equals 1 right here, this actually evaluates to 5. And of course, that's a prime number, all right? So we have one solution right here. Okay, 1 times 5, and this is more or less the definition of a prime number. But notice that if it's anything else, if this part right here will always be greater than 2. Okay, this piece right here will always be greater than 2, and then this piece will always be greater than or equal to 5, right? And so this really is the only solution. And again, what I'm trying to say here, this part, this piece right here, that I hope it'll let me circle, is always going to be greater than or equal to 2. Or it's just going to be greater than, I should probably just say greater than 2, but let's just say greater, that's good enough to say greater than or equal to 2. If you choose unless this happens, unless a is equal to 1 is equal to b, this expression right here is always going to be greater than or equal to 2. And this is, again, when a is not equal to 1. Okay, that means it's got to be greater than or equal to 2. Okay, so you see, we've actually found the only solution. It happens when a equals 1, b equals 1. And so a single answer to this question is this value for a and b, and the prime number that we get is 5. Sorry for it being so slow.